we've got all the information that we need to do the compass error and azimuth calculation now, because the A and B formulae require LHA and declination and latitude, so we've got all of that information, and then obviously we can work out C from there and then work out the rest. So let's have a look at working out A first of all. So the formula for working out the value for A is tan latitude over tan LHA. And it's simply a case of keying that into our calculators. So tan 11 degrees 19.7 divided by tan 333 degrees 58. And can you see that the number there comes out negative? We're just going to knock that minus sign off. If you're keeping things in your calculator for use, you know, later, so you don't have to key them in again, just multiply that by -1 and it turns into a positive number, because that's what you need it to be. You don't want to put it in as a negative number. And I'm just going to note that down: 0.410139845. I'm then going to work out value B. So this time I'm going to use the tan of the declination over sine LHA. So my declination is 15 degrees 48.4, and you're going to divide that by sine 333 degrees 58, and that again comes out negative. We just want to get rid of that, and you end up with 0.645024021. The reason we got rid of those minus signs is because we're not going to determine what we do with these numbers on the basis of whether they're positive or negative. We're going to determine what we do with them based on the names we're going to give them. So you need to name A and B north or south. Let's start with A. There's a rule that's actually reproduced in Norrie's that tells us how to name A, and the rule is that A is named opposite to the latitude except for when the LHA is between 90 and 270. So if our LHA is anywhere between 90 and 270, we would name the A value the same as the latitude, otherwise we're always going to name it opposite. And in this case, our LHA is definitely outside the 90 to 270 range, so we're going to name A south, opposite to the latitude. B is much easier to name than A. B is simply named after the declination. So here we've got a northerly declination, so we're going to name B north. And because these two have different names, that dictates that this is going to be a subtraction in order to find the value of C. Had they been the same, we would have simply added them together and named C after both of them. But because they've got different names, we're going to have to subtract the smaller one from the bigger one and name the resulting value, C, after whichever one was larger. So we can already see here that our C is going to be taking the north name because B is a larger value than A, and B is named north and A is named south. So it's going to be, our C is actually going to be north. So I'm going to subtract the A value from the B value now. Which gives me a C value of 0.234884176. And that's going to be named north. The next step is to find the tan of the azimuth. So if you go to your formula sheets, you'll see that to find the tan of the azimuth, the formula is 1 over C times cos lat. So that's just what I'm going to do here. I'm going to say 1 divided by, open bracket, use the answer, multiplied by cos 11 degrees 19.7. And the answer that I'm getting for my tan ASI is 4.3 3, 4, 2, 0, etc. Now, I can write that down if I want to, but really what I'm interested in is doing an inverse tan and finding out what the azimuth actually is. So 77.03, so I'm just going to call that 77.0 and just round it to the nearest decimal of a degree. That in itself doesn't actually tell me what the true azimuth is though, because that's just the size of the angle measured from the north-south line, basically measured from the meridian. That's what an azimuth is. So to turn that into a true azimuth, I need to work out how to name this. Now the first bit's easy because it comes from C. The first bit of my azimuth is actually just whatever C's name is, so my first bit's going to be north. The next bit depends on the size of the LHA, because if the LHA is between 0 and 180, this is going to be a west azimuth, and if it's between 180 and 360, this is going to be an east azimuth. In this case it's between 180 and 360, therefore I'm going to name it northeast. Luckily for us, a northeast azimuth is simply the same as the true azimuth. Do you remember what we were looking at before, where we imagined that all the angles that the azimuth could be, they're going to fall into one of the quadrants, and in this case it's the angle in the northeast quadrant, and you can see there that that angle there will actually equate to a true bearing, so you don't have to do any further calculations for that. It's simply northeast, or 077.0 degrees true is your true azimuth there. There's a space for the position line on here, so the position line, remember, runs perpendicular to the azimuth. So 77 plus 90 will give you one end of the position line, so 167. You can see that if you try and subtract 90 from 77, you'll get a negative number. So there are a couple of ways to look at this. One of them would be just add another 180 to 167 to get the reciprocal end of that bearing. The other would be to subtract 90 from 77 and then add 360 to make it up to a positive number. So I'm just going to go for the adding 180 approach to find the reciprocal of 167, which is 347, and that's my position line for the sun. And of course you could then go on and use that in a plot.